Okay, it is a couple minutes after 11 and the Saturday sirens are over, so let's go ahead and get started. For those of you who are here for the first time, I'm Dave. I'm the outreach coordinator for the Department of Physics and Astronomy here at good old Purdue, and we welcome you. I have a couple of other people I will introduce. Professor John Finley will actually talk to us in a little greater length here in a little while. Good morning, Professor Finley.
Good morning, everyone. It's a beautiful Saturday.
Professor Finley is an expert. He's the head of the department, first of all. He is an expert on stars and many other things, cosmology-wise, and so we're happy to have him here. And then Vic Dong. Vic, good morning. Would you like to say hello?
Hi, my name is Vic. I am a senior here at Purdue, majoring in physics. And yeah, I've been with SMAP for like a while now, so.
I would say at least 3 years.
Yes.
In fact, I don't know if you noticed the tweet that I sent out yesterday, but you're featured in that because you did this very lesson with us about 3 years ago. So,
oh, I didn't see that.
It's also the thumbnail for the YouTube live stream, which we're doing concurrently. So you have a little fame out there. So thank you for your years of service. Vic will be graduating here shortly, and she will go on to earn a PhD in astronomy, astrophysics?
Yeah, in astronomy.
Great. Well, I hope this won't be the last time we see you in SMAP. So I hope we can stay in touch.
For sure.
Okay. So we're going to ask maybe some questions here as we get started. I didn't do a poll. I'm going to have you just use the reactions and raise your hand, either visually or use the reactions and put up a hand. We'll do that here in just a minute. So, excuse me, for the educators that are with us, or if you want to know how we got started, we've done the lives of stars for probably 4 or 5 years here in SMAP. Face-to-face on campus. And then when we do that, we actually, we print out these large HR diagrams and then have students use stickers that we purchase to complete them. And they work in groups of 3 or 4 or 5. But for the remote environment, we scrunched things down a bit and created the same image just on a printable 8.5 by 11 sheet. And instead of using stickers, we provided students with a sheet that they can cut out the dots and either glue them or tape them on their HR diagram. So any teachers interested in the details can contact me. So for the students here, I'm interested in your thoughts on the lesson. What kind of short comments would you have? Did you have any issues with the materials we sent out? Did you have anything that was difficult? Any problems with the simulation? Was anything confusing? Give me a little feedback. You can unmute yourself and just talk. That'll be fine.
Is it cool if I go?
I'm sorry?
Is it cool if I say some stuff about the?
Yeah. Yes, please do.
Okay, so first thing I wanted to say about the star in the box is that for the lower mass stars, I found that the time moved really quickly.
It does.
So for my time, I used 9 million years, and like you'd play it, and then like instantly it'd be at like 4 billion years or whatever.
Mm-hmm.
So that was one thing. And then the second thing was I just wasn't a fan of the cutting and pasting of the little circles.
It's a little tedious, I'll admit. Doing it with stickers is a lot more convenient, but we didn't have stickers to send out, and so we went with the cutout circles. So yes, and you know, when you run the simulation, you can slow it down, but even when you slow it down, the larger mass stars go by really quickly. So it's a little hard to zero, but Nicholas, what that tells you is that it doesn't really matter. So if your target is 9 million years and you end up at 40 million years and you haven't left the main sequence, that's fine, because the star hasn't gone anywhere. It hasn't moved off the main sequence. So those are good points, though. What does anybody else have? Any other comments? Okay, I'll take that as no other comments. Thanks, Nicholas, for your suggestions. So let's have a little fun. I've got a few questions for you. So these will be fact or fiction questions. So I'm going to ask you 4 or 5 questions. Raise your hand or use the reactions to respond. I'm going to have you respond if you agree and think that this statement is correct, okay? Fact. All right, first statement. As stars migrate, as stars age, as they get older, they migrate up and down the main sequence. Fact or fiction? If you think that's correct, you think that's a fact, show me. Okay. If you don't know, you can show me. But that is fact. I'm sorry, it is not fact. They do not migrate. A star is created by a process, and they end up on the main sequence, and they are there for their lifetime. Now, when their fuel begins to expire, they will not move up and down in the main sequence. They will move off the sequence and then go other places in the diagram, but they do not go up and down the main sequence. So if you thought that was, thought that my statement was false, good for you. Okay, here's the next question. Larger stars last longer than smaller stars. If you agree, if you think that's fact, let me see. I don't see anybody agreeing with that. That's good. In fact, larger stars have more mass, they have more fuel, they burn hotter, and they burn out more quickly. So you could learn that from the star in the box. Third question. Stars located higher on the main sequence are hotter and brighter. Fact? Okay, we're good. That is in fact true. And again, you can learn that from the star in the box. One last question. Blue stars are hotter than red stars. Fact or fiction? Fact, raise your hand. Blue stars are hotter than red stars. Okay. You're good. You actually learned something. That's great. So before we introduce Professor Finley to take the lead here, I'm interested in your diagrams. Now, a couple of you have sent me some photos, but if you have diagrams, if you did 2 or more, can I see them? You don't have to show your face if you don't want to, but I would like to see. All right. Drew, how are you this morning? Did you have any diagrams? Did you get a chance to do that? Avi, did you have a chance, or did anyone run out of time? Okay, I see a few people that say they didn't have time. I understand that. It's the end of the semester, school's almost over. You have a lot of other things to do, and you don't have to have done the lesson in order to join us, so it's fine. Let me just ask you a question. Here are two examples of the HR diagrams from the materials we sent you. Here's the first one. Here's the second one. These both represent 10 stars in a cluster. First one, second one. Which diagram represents stars, represents a longer age of the stars? The first one or the second one? How many would say the second one is the longer age for that cluster of stars? Okay, I see hands, I see comments, you are correct. So we may come back to the HR diagrams and ask some more questions a little later, but for right now, I would like to introduce to you Professor John Finley, who is going to, excuse me, who is going to talk a little bit about the HR diagram, the lives of stars, and some other very interesting facts. I've seen what he has to say, and I think you're going to like it. I will also tell you, if you have a question during the presentation or any time moving forward, just pop it in the chat, say I have a question, and or unmute yourself, and it's okay to say, excuse me, I have a question. Either way, we'll be fine. We want to answer your questions as much as we can. Professor Finley, are you ready?
I'm ready.
Okay, then I'm going to hand the show over to you.
Okay.
Let's see what you have to say.
So thank you everyone for coming. I have been at Purdue for 28 years, and I've been doing astrophysics now for 35 years. So it's a fascinating subject. There's always something more to learn. I am going to share my screen with you, and I'm going to be sort of interactive. So I'm going to be asking some questions. So if nothing else, everybody should at least unmute their audio. Let me see if I can share my screen. PowerPoint slide, it says. Okay, can you see that?
I can see that.
Excellent. Good. So let me, first of all, let me expand my, I want to look over here, but unfortunately my PowerPoint's over here. So, so you basically did this exercise with looking at the luminosities of stars and their temperature, and then plotting them in the appropriate place on what's called an HR diagram. So I want to point out what this diagram is and why it's important. So first of all, you notice that you plotted on the vertical axis the luminosity, not the brightness, but the luminosity. Does everybody know the difference between brightness and luminosity?
Luminosity is the power and brightness is how bright it is.
Yes, that I can take that. Luminosity is the power. It's the amount of energy per unit time that the star is producing. Whereas brightness is the quantity we measure when we measure it on a telescope. How bright is it? Now, the problem with brightness, as you may infer, is that I can have a really bright star, but I can put it, or I can have a really luminous star and put it very far away, and it therefore then has low brightness. So if I plotted stars versus their brightness on an HR diagram, I'll just get a mess, right? Because I don't know the critical important ingredient, and that's the distance to that star. Now, let me, before I go on and tell you how important distance is. So on the horizontal axis, you plotted temperature. And by the way, there are multiple proxies for things like temperature and luminosity. So for temperature, one of the proxies is this thing called the spectral class, O, B, A, F, G, K, M. Basically, the spectral class tells you how hot that star is. So you can plot an HR diagram, not with temperature, but with that spectral class as well. You can also plot it with this thing down here called the color, right? It's called the difference between the blue color and the visual color. And that is also a proxy for the temperature. But you were dealing with temperature and luminosity. So how would you measure the distance to a star if I gave you that as a task? Or does anyone know how they measure distances to stars? No? Yes? No? Okay, so let me show you one of the surefire methods that you can use to measure the distance to a star. It's called parallax. So I would like everyone, I'm going to back away a little bit so I can get my hand out. Everybody put their hand out like this with their finger up. You know, full stretch of your arm. Now close an eye. Close one eye, left or right, I don't care. Okay. Now, focus on something in the background. A picture, you know, something on the wall, something on the background. Okay. Once you're focused on that, and now close the eye that's open and open the other eye. Did you see how your finger shifts back and forth relative to the thing you were focusing on? Everybody? Yes? Nicholas, you got it? Did you see that? Okay, Daniel as well?
Yes, sir.
Okay, good. Abby and all right. And I'm sorry, what's your name? Bar, you're muted.
I'm Drew.
Drew, okay.
It didn't log it in right, but yeah.
Gotcha. Okay. Okay, good. So that's called parallax. It's basically the shift of a nearby object depending on the angle at which you're looking at it. So if I gave you a very good telescope and made you put it on a satellite, satellite's good because you're above the atmosphere. Atmosphere messes up images. And said, now go and measure all the stars within 300 parsecs. Okay, good. Now there's a word, parsec. Anybody know what a parsec is?
Is it 3.26 light years?
It is. And why is it 3.26 light years and not something else? You know that? No is an okay answer.
I forgot.
Parsec is short for parallax second. So it's the distance a star would be from the Earth to have a parallax, i.e. a shift against the distant background stars, of 1 arc second. So parsec, parallax second. So if you do that and you measure, so as Daniel said, it's 3.26 light years. It's a parsec. And it's just geometry. You can sort of calculate that yourself. It's just, so now I say, okay, go out and measure all the stars within 300 parsecs. Well, that's about 1,000 light years, right? And what you would get is the following. So that is an HR diagram of all the stars measured by an instrument called Kepler. And basically, they got the distance to all of these stars. The distance allowed them to know the luminosity. Right. So here you can see a beautiful, developed main sequence. You can also see some of the things that left the main sequence, as you saw in your simulation. So here are some giants. There's a few supergiants. There's some bright giants. These are called by the way, luminosity classes. So 4 is a subgiant, 3 is a giant, 2 is a bright giant, and so on. The stars on the main sequence are luminosity class 5. They're also called dwarfs, right? Because they're basically smaller stars than all these ones up here. And you even see within that 1,000 light years, a bunch of white dwarfs. So that's the HR diagram. That's probably one of the best determined HR diagrams ever made. So what is this HR diagram? Why is it HR? Well, it's named after 2 astronomers. One of them is Einar Hertzsprung. He was, I believe he was Finnish or Norwegian. And Henry Russell. Independently, they were working, and they realized that there was a relationship between the luminosity and the temperature of a star. And basically, once they sort of realized there was this relationship, they could then figure out how stellar evolution happens by where a star goes in this diagram. So let me point out a couple of stars here. Here's Betelgeuse. Does everybody know Betelgeuse? Okay, Betelgeuse is the star that's in Orion's shoulder. Now, unfortunately, you might still be able to catch Orion, maybe right after sunset in the west. But anyway, Betelgeuse is the star that's in Orion's shoulder, and it's Orion's right shoulder. Betelgeuse is one of the few stars that when you look at it by eye, looks red. Have you guys seen Betelgeuse and said, whoa, that's red? As opposed to all the other stars sort of look blue or white. Betelgeuse looks red. Now, why does it look red? Well, it's because it is huge. It's a gigantic star. It is 1,000 times the radius of the sun. Okay, 1,000 times the radius. Now, the sun, of course, has one solar radius. And inside a solar radius, you can fit 1,000,000 Earths. Okay, so if you had 1,000,000 Earths, you could put them inside the sun, neatly stacked, and they would all fit. That's how big the sun is. Betelgeuse is 1,000 solar radii. And of course, volume goes like the cube of that number. So it's actually 1 billion times the volume. So you would be able to put 10 to the 15 Earths inside of Betelgeuse. That's how big it is. And the fact that it's so big, it's not that far away either, actually. It basically looks red. So on this main sequence, which is called a zero-age main sequence, you see that there's lots of, in fact, there's a lot of stars on this slide that are basically named so that you can go look them up if you want. And they have various lifetimes on this diagram, as you found out from your simulation. So stars down here have very long lifetimes. In fact, stars down in this area Some of them haven't even had enough time to form yet. Others have lifetimes longer than the age of the universe. So they basically look just like they were when they formed. Until you get all the way up to, well, this goes up to 10 solar radii. So lifetimes, little less than 30 solar masses. Those have lifetimes of 10 million years. Now, in the scale of astronomy, 10 million years is fairly short. Okay, so just to give you a sense of that scale. So you could also see here are the giants, here are the supergiants, and then here's some white dwarfs. And basically, let me get to that. Stars actually differ enormously in the size, as you can see from that previous plot. Right, so you go from 1,000 solar radii. These guys down here are 1/10 of a solar radii. Right, so they're small, very small, whereas these are gigantic. So they vary a lot. It's also one of the hardest things to measure is the size of the star. And as I said before, stars that are on the main sequence are called dwarves, and the ones off the main sequence are typically giants. The luminosity of a star is related to its size. So here is 4 pi r squared. Does everybody know what that is? 4 pi times the radius squared. Somebody? Abby, what's 4 pi r squared? You can use the chat if you want. Drew? No?
So I know that pi r squared is the area of a circle.
Yes, okay. So 4 pi r squared is the surface of a sphere. It's the surface area of a sphere. Right? Of course, the bigger r is, the larger the surface area, also larger the volume. So the luminosity depends on the size of the star. So this is a quantity here, 4 pi r squared, that points out the size. And this quantity here is the temperature to the 4th power. This is a fundamental constant called the Stefan Boltzmann constant. It's just a number for now. We don't have to worry about it. So the luminosity depends critically on the size of the star and how hot it is. But notice this is a 4th power. It's a very, very strong relationship. So that's why these stars up here are so much more luminous than the stars down here, right? It's because they're hotter, and that temperature goes like a 4th power. It's a pretty big power. So keep this in mind: luminosity, size, and temperature. And size and temperature. It's all well and good to have stars on the main sequence, but you have to ask yourself the question: how did they get there? Right. So basically, right now, at this epoch of the universe, in our galaxy, there are lots of gas clouds. So here's a gas cloud here. This particular one is the Carina Nebula. It's in the constellation Carina. And you can see lots of features in here. This is a Hubble Space Telescope image, pieced together, many, many pictures taken and then put together. So you can see lots of features in here, things that look like circles, really dark areas, little blobs sort of floating around by themselves, things like this. I want to point out to you that this is the birth, this is the basically of the stellar nursery. This is where stars get born. You start with a bunch of gas. At some point, the gas will condense. Once it condenses, gravity takes over and starts pulling in more material, more material, more material, and builds up a star. So let me point out here, for example, you see this little, does everybody see what I'm pointing to? This little blob here? Whoops, sorry. I gotta make sure I don't click on that. There's a little blob here sticking off of this, this piece here. That blob is where a star is forming. To give you an idea how big that star forming region is, that little blob there is about 100 times the size of our solar system. Likewise, this here, 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 they're all over that place. So this is a huge feature that's producing new stars. Now, how does a star go from being diffuse gas to a star? Well, it has to basically condense. And when it condenses, it gathers more and more mass. And it follows a track on the HR diagram, log luminosity versus log temperature. So this is a logarithmic scale. You're used to that. Your HR diagrams are logarithmic. So here is for a typical star, around a solar mass or so. This red line is called its Hayashi track, named after the astronomer that sort of theoretically worked out how stars will move on the HR diagram when they're forming. Now, this is interesting because notice this Hayashi track, right, is at virtually a constant temperature, but its luminosity is going down. So what does that mean? It's at a constant temperature, but its luminosity is decreasing. And let me remind you of that equation. Luminosity is going down at a fixed temperature. So what else has to go down?
The size of the object.
Exactly. It is condensing. It's getting, whoops, went the wrong way. It's getting smaller, right? Smaller it gets, the less luminous it is. Okay, good. Now, it keeps doing that until in the core here of the star, the core at the very center, it actually starts to generate energy. So now it's starting to make its own energy. That energy has to come out somehow. And so as it's coming out, of course, it's now increasing in temperature because it's generating more energy. And of course, it's going up a little bit because it's going to puff up a little bit, right? That energy that is being produced in the core is pushing the star out. At some point, we get fusion to occur in the star. And that's when it lands on the main sequence and spends its life there, happy and content. Here are various Hayashi tracks for different mass stars. So here is a one solar mass star like this one. You see it drops. I did it again. Gotta stop doing that. It drops down, makes that little left turn, and then lands on the main sequence. Once it's on the main sequence, it's very content and happily making energy in its core and balancing gravity. Here's a 3 solar mass star, here's a 10 solar mass star, and here's a 100 solar mass star. Notice the times here. These are the times it takes for the star to condense. So a really small star would take 100 million years to condense before it gets to the main sequence. The sun took about 1 million years to get to this little point, and this part's very fast. Big stars, like ones that are 100 solar masses, take a very short amount of time, 10,000 years. So that's an evolutionary track that they follow, and basically this tells you how the temperature and luminosity change with time on this track. So notice this one here is almost at constant luminosity. Now, what happened to my... Well, for some reason, I lost your pictures. All right, whatever. This is the core of a star, about the inner 10% of the star, where it's generating energy. And it's generating that energy, which is pushing the star out. But gravity always pulls stuff in. It's trying to pull the star in. So the way they get to the main sequence and why the main sequence is there is because those stars are in balance. They're in equilibrium. They're producing exactly the same amount of energy needed to balance gravity pulling it in. If the core stopped producing energy, gravity would win and pull it together. If the core produced more energy, the core would win and push the star out until it was again in balance. So it's a balancing act that nature is doing. So our sun has existed for about 4 billion years, almost 5 billion, and it'll last for another 5 billion. And if it's going to be in that constant state, which it is, it doesn't really change, then it has to be in balance to last that long. Now, the problem with a star is we only see the outer layer of the star. We don't see the core. We only see this outer layer. But physics tells us that the amount of energy that's leaving the outside surface has to be equal to the amount of energy made in the core. Now, why is that? Anybody want to offer? Why does that have to be the case? Energy flowing off the surface has to be balanced by what's being generated in the core.
Isn't it because of the law of conservation of energy?
That's correct. Absolutely correct. If it wasn't, that means energy would build up inside here somewhere. If it was producing more energy in the core and it wasn't equal to what's on the surface, then you'd have a buildup of energy in the core and something bad would really happen. So conservation of energy tells us that the amount of energy leaving the surface is equivalent to what's being produced in the core. Okay, good. Now, what is actually producing that energy is the question. What's producing that energy is, oops, again I did that. Again I did that. What's called nuclear fusion. So basically, if I said to you the universe is made out of almost all hydrogen and asked you if that was fact or fiction, what would you pick? Fact or fiction? Who thinks it's going to be fact? It is a fact. It's for the most part, the universe is made out of hydrogen. It's about, in the local neighborhood, 76% of everything is hydrogen. 26%, 25.5% is helium. The rest of it is everything else, you know, the carbon, the nitrogen, the oxygen, the calcium. So most of the universe is made out of hydrogen. And in fact, most stars are predominantly hydrogen. So that means in the core, there's a lot of hydrogen. The core is very hot, 10 million degrees Kelvin, and it's very dense, about maybe 10,000 times, 10,000 grams per cubic centimeter. Now, just out of curiosity, what is the average density of the sun? Anybody have any idea? The average density. It's mass per unit volume. No?
One
about-
solar mass per solar radius.
Yes. Per cubic solar radius. That's good. Yes, it's true. But how much is that? What is that number? If nobody knows, that's fine. Because I'm going to tell you, it's 1.4 grams per cubic centimeter. And what's that close to? Anybody know what has a density of 1 gram per cc? Water. Water is 1 gram per cc. Essentially, any fluid you find on Earth is going to be almost 1 gram per cc. You know, there's a few things that are more dense than that, like maybe maple syrup or glycerin. But, you know, all the other fluids are all around 1 gram per cc, about the density of water. The sun is basically almost the density of water. It's a little bit more. So the sun is like a big fluid ball, right? It's a big fluid sphere. And deep in that core of that sphere, at 10 million Kelvin, it's able to do this interaction. Two protons, which are hydrogen nuclei, interact. They're pushed together because they're moving very fast and they're very dense. They interact and they produce a positron, which is a positively charged electron, and a neutrino. If you've never heard of a neutrino, don't worry about it. They're curious little particles that don't interact with matter at all. When that happens, and the reason there's a positron and a neutrino is one of these hydrogens turns into protons turns into a neutron, forms a deuteron. It's called a deuteron, which is a bound state of a proton and a neutron. Chemically, it's called 2H because it has the chemical properties of hydrogen, but it has the extra mass of a proton. So it's 2H, 2 atomic mass units. Now, that deuteron, I'm going to call it deuteron, that deuteron can interact with another hydrogen atom, hydrogen nucleus, or a proton here. Right? So they get rammed together. When they do, whoops. When they do, they produce a gamma ray, a very energetic photon. Okay. And the product of that interaction is you form helium-3, bound state of 2 protons and a neutron. Now notice there's no positron and neutrino in this interaction because I didn't change one of the protons to a neutron, but you get out energy. That's the energy right there. In fact, that is the energy that comes off the surface that we see, that produces our visible light. The last step in that interaction, this is the dominant energy producing, is to have 2 of those helium-3s interact and produce a helium-4. This is normal helium. And in the process of doing that, notice there's 1, 2, 3, 4, 5, 6 particles involved. You get back 2 of those hydrogens. Okay, so you get 1, 2, 3, 4, 5, 6 hydrogens. fuse to produce one helium and two more hydrogens. So that process goes on in the sun, in the core, and it lasts for 10 billion years. Now, you're not going to know this, but I'll give you an idea. Give you an idea how big the sun is. The sun is fusing, so it means doing this process and consuming 100 million, right? So that's 10 to the 14, 100 million metric tons of hydrogen every second. But there's enough of it in there that it can last for 10 billion years. It's just a staggering number, but it's what it is if it's going to balance what's in the core to what's on the surface. So the energy that we see that, you know, warms our planet, keeps our days bright, come from these photons, right? And how long do you think it takes for them to get from the core to the surface? Let's take a guess. What do you think? Daniel, what do you think? Core to the surface, that photon. Nick? Guess?
1,000 years.
1,000 years. Why do you say 1,000 years? Out of curiosity.
Well, that energy needs to go through all of the matter, right? And the more matter you have in the way, the slower it needs to go.
Oh, very good, very good, very good. You buy into that, Drew? Sounded reasonable to me. That's actually exactly what's happening, except that it takes 200,000 years in the case of these photons. So the photon that's created in the core, this is basically, I call it rattles its way out, right? It's interacting all the way as it goes. And this particular process is called a random walk. And it random walks through the core of the star, all through the outer layers, and eventually gets to the surface. Now, each time it interacts, it produces other photons that are lower energy. So the energy that's being generated is getting degraded each time it interacts. So that those photons here are about 1 million times as energetic as optical photons. So I've got 1 million times optically energetic photon. By the time it gets to the surface, it's 1 million optical photons. And that's what we see streaming off the surface. Remember those neutrinos in that process? I said they don't interact with matter, which means it only takes them 2 seconds to get out, right? Because that's basically the light speed size of the sun, right? It's 2 light seconds. So those neutrinos, if you can measure them, will tell you directly what's going on in the core. These photons cannot, because every time they scatter, they lose a little information. So by the time you get to the surface, they've forgotten where they came from. That would be this 2 seconds for the neutrinos would be the maybe the meat for another talk. So now, how do you know everything I told you is true? Or why would you believe me? Maybe it's all fiction. Maybe I just made it up. Right? Well, you can test all these ideas. So one way you can test it is to go and measure luminosities versus temperatures for objects you know the distance to. And one way you do that is to look at things that are called clusters. You know what this cluster is? Can you tell what that is?
Pleiades.
That's the Pleiades. In the sky, it looks sort of like a tiny little Big Dipper. And if you have really, really good eyes, you can see 7 stars in the Pleiades. I can only see maybe 5. But there are people, that used to be the way they would test somebody for navigating the desert at night. Can you see 7 stars in the Pleiades? So here's the Pleiades. They're sitting inside their birth area. So all of this is the gas they were born out of. It's blue because these are very bright stars. These are probably 10 times the mass of the sun, 8 to 10 times the mass of the sun, these brighter stars. And they ionize all the gas around them. When you ionize gas, when it recombines, it glows blue. And here is a measurement of, these are data points, so these are just measurements of the luminosity versus the temperature for the Pleiades. So looking at that HR diagram for the Pleiades, what does it tell you? Nick, you did the exercise. What does that tell you?
It shows you that all the, or most of the stars in the Pleiades are part of the main sequence still, right?
Right. And what does that mean? That means it's relatively young. In fact, this is called an open cluster because it looks sort of spread out. And these are relatively recent additions to our galaxy, right? These obviously have just formed recently, and therefore they have a fully developed main sequence. They're young. Another laboratory you can look at is what's called a globular cluster. So here's a globular cluster. I believe it's M55. These you find, so those open clusters you find in the galaxy, the globular clusters you find sort of surrounding the galaxy in a halo. These are old. They're old. They were remnants from when the galaxy formed. So you can go and you can measure the luminosity versus the temperature. These are important because notice they're all bound together, right? It's a big ball of stars, which means they're all at the same distance. So I sort of eliminate that problem of how do I measure the distance? They're all at the same distance, which means I can measure the brightness, and I know that that brightness relative to all the other stars is meaningful and is reflective of the luminosity. So now here's the main sequence for M55. So you notice that it's got all its young stars, and then at some point at a color of about 6,000, that's about 1 solar mass, the stars are now leaving the main sequence. And there's even some here that are sort of making their way down to the white dwarf area. These are a particular odd category of stars. They're called blue stragglers. And nobody's really sure why they do what they do, but there they are. So this fact that there's a turnoff, this is a turnoff, tells you this is an old cluster. And that cluster turnoff point is about the age of a star that's around 6,000 years or 6,000 kelvins. So, you know, roughly 10 billion years or so. So that's a very well developed giant branch. By the way, if you nose around in
Sit on the bicycle.
if you nose around on the Hubble Space Telescope site and you look up planetary nebula, that's where all the planetary nebula live in this. The planetary nebula from a giant to a white dwarf. So I go back to that image of the Carina Nebula, and I'm going to leave you with one stunning fact. So in that Hayashi track, when I was forming stars, the main sequence only went up to 100 solar masses, right? So why did I pick 100 solar masses? Well, it's not a short story, and so I'm not going to tell it, but you'll have to take my word for it. That's about as big as a star can be. Bigger than that, they basically fall apart. They're unstable. So if I look in the Carina Nebula and focus in on this area that I've boxed out, and then look at that area, so you can see here's that sort of triangular looking thing. And I want to focus in particular on this object or this spot right here. And now I'm going to go and get the Hubble Space Telescope again and take a close-up view of that spot. And that's what you see. This is the called Eta Carina. Eta means, what is that, 5? It's the 5th brightest star in the Carina Nebula. This star buried in here is just about 100 solar masses. This is as massive as a star can get. And the reason it looks the way it does, remember I said it's unstable if it's much more than 100 solar masses? This is right on the edge of being stable or unstable. So it's essentially shaking itself apart. It's doing this all the time. So it's blowing itself off into the interstellar medium. So these two big blobs are the surface of the star as it's being shaken off. So 100 solar mass is about as big as a star as you can make. Of course, a 100 solar mass star won't last real long. So we're actually lucky that we could even see this, right? Because they are born and die in a very, very short amount of time, 10,000 years or so. So that's what a 100 solar mass star looks like. There's actually an argument for this, what the smallest star can be. It turns out it's about 100 times the size of Jupiter, but that's a different story. And I think that's all I had. And I'll take any questions you might have if you wish.
I have a question.
Certainly.
So I know that as dwarfs go into like red giants, they usually begin burning helium instead of hydrogen.
Correct. Well, they develop a helium core depending on how big they are.
Okay. So my question is if they become white dwarfs, do they change what fuel they burn, or is it also just hydrogen or helium?
Well, a white dwarf actually technically isn't a star. It's no longer burning anything. So it's the core of one of those big giant stars. So like our sun, for example, at 1 solar mass, will never burn helium. It's not big enough. It'll never get hot enough to do that. So when our sun transitions to the giant branch, it'll form a helium core. The thing that makes it blow up, get really big, is the fact that all of the hydrogen sitting above that really hot core now, because the core shrinks and gets much hotter. So it starts to generate much more energy more rapidly, and that's what causes it to blow up. You need to get about 3 solar masses before you can burn helium. And then if you want to go beyond that, you have to get even up to above maybe 8 solar masses, where then you can start burning things like carbon and nitrogen. A white dwarf is basically burning nothing. It's basically a cinder. It's an interesting cinder because it's pure helium for the most part, and it's just cooling off. So it starts around whatever the core temperature was, 10 to the 8 kelvins, and then cools off to ultimately 0 Kelvin. Does that answer your question, Nick?
Yes, thank you.
Others? Oh, you must have at least one other question. Come on now.
Professor Finley?
Yeah.
How about stop sharing your screen so we can
Oh,
see you full size?
I forgot to stop sharing. There we go. Sorry.
I'm going to ask the question until someone else has one they want to ask. You refer to the Pleiades as being an open cluster. I think of the Pleiades as a constellation, and we know that when we see constellations in the sky, we somehow have this mental picture that they're kind of in the same plane, when in reality, stars may be light years apart. We just see them from our perspective to be in kind of on a plane. Are the stars in the Pleiades close enough in proximity that they must be close enough in proximity to be really called a cluster?
Correct. They are close enough together that they are gravitationally bound. They're all rotating around their center of mass. And the Pleiades is one of the unique objects where it's both a cluster that's, in other words, all the stars are at the same distance, and it's a constellation. Most constellations, the stars in them, like the Big Dipper, for example, or Orion, they have no relationship to each other at all. Because, of course, when you look at the sky, you're looking at a 2D projection of a 3D volume. So, for the most part, constellations are just happenstance arrangements of bright stars on the sky. The Pleiades is a little different because, yes, it is a cluster, and it's a bright cluster that's relatively nearby. So it was named a constellation, the Pleiades, the Seven Sisters.
Okay, thank you.
I forget the mythology behind it.
How about a question from anybody else? Anybody else have a question? Now's the time. You've got an expert.
You may never have this opportunity again. Oh, wait a minute. There's something in the chat. I'm not paying attention to the chat. Daniel left and rejoined. Sounds good. No. All right.
I think we're up to date on the chat.
Yeah, I think so.
So while people are thinking, I've got a couple of things I'd like to throw out. First of all, the way we've been doing SMAP has been, as you know, we send out the materials a week or so ahead of time, give you a lesson to do, and then we talk about it live. I'd like to ask those of you that are here, is that a good model, or is there a better way that might be better for you to do Saturday morning astro? So what I'm thinking is, another option would be that we do something in real time. So instead of sending you this lesson 10 days ago, we could have done it in real time with you this morning. And it might take a little longer than an hour that we normally allow. Would that be a better model, or do you like the current model? And you don't have to answer that now particularly. You could email me and let me know. I just want to make what we do as convenient for you as we can. So if you have some thoughts on that, you can let me know. And before we wrap up, I have another question for Professor Finley. I assume that you didn't come out of the womb a scientist or interested in science. And I would be interested, for the sake of the younger people among us, to know what kind of, what point in your life and what kind of influences directed you in the path that you've chosen.
I had an interesting path to becoming a physicist, astrophysicist. I basically in high school was much more interested in literature and history than I was in math and science. I actually was good at math. I actually got good grades in math, but it just didn't interest me at that time. When I graduated from high school, I could not afford to go to college. So I had to sort of, make my way through the world for 6 years before I was able to get on programs and get Pell Grants and things of that nature so that I could make my way through college. Now, during that 6 years, like remember I said I was into literature and history. I started reading some books that were popularized science at the time. One of them was called The Tao of Physics. Another one was called The Dancing Woolly Masters. And it was all about quantum mechanics and how strange quantum mechanics was. And when I read that, I was also a big science fiction fan. I said, my God, this sounds just like science fiction. Can this really be real? So when I basically decided, because working in factories is not fun. When I basically decided, well, I maybe should go and get a college degree so I don't have to work in factories. I thought, well, maybe I'll try that physics stuff. It sounded sort of interesting. So I would say it was probably when I was in my early 20s, early to mid 20s, when I decided I'm going to be a scientist. Now, like I said, fortunately, I was pretty good at math when I was in high school. Unfortunately, I only had the basic math. I had algebra and trigonometry. Never had calculus. So, I had a tough road ahead of me. I had to learn not only the physics, but all the calculus too beforehand. So it was a challenge. However, I had the support of my wife, and I just stuck to it, and then realized, I couldn't figure out when I was doing my studies, what did I like the most? Did I like, particle physics? Did I like electricity and magnetism? Did I like quantum mechanics? And when I got into graduate school, I ended up going to graduate school. I realized that if you do astrophysics, you do all of those things to sort of understand how systems work that are astrophysical. So for example, today you heard me talk about gravity, right? Pulling the star in. Nuclear fusion, that's sort of quantum mechanics. Electricity and magnetism, right? Because they're charged particles and they have to get shoved together. And I didn't mention it, but there's also thermodynamics in there too, because stars are ideal gases or they're not ideal gases. So I realized, well, astrophysics is pretty good. I can do all of those things and not have to choose one or the other. So that's what sort of led me down the path of astrophysics.
Thank you for your story. It's an interesting one. Does anyone else have a question? We'll wrap up and send you on your way, but I don't want to preclude a final question. Anything on your mind? Okay, then. With that, I'd like to thank Professor Finley. I would like to wish Vic a happy voyage on the next chapter of her life. And thank you all for participating in Saturday Morning Astrophysics at Purdue. We'll see you next time.
Thank you for coming, Nick and Drew and Daniel. And I think Abby left. Okay, see ya.
Thank
All
you.
right. Bye-bye.
Thank you. Have a great day.
Thanks.
Thank you. Bye.